Hi, y'all. A little change of scenery here, trying to get away from the noise. So we are going to talk about today the magnetic field that's created by a circular coil of wire that's carrying current. Specifically, right smack dab in the center of that circular coil of wire. And we're going to show a video first. I think I managed to have the sound off for this one. I know in the last one, the background noise was really bad because of the sound in the video. Um, but what we're staring at there in the YouTube freeze frame is not actually a circular coil of wire. It's what's called a solenoid. Circular coil of wire instead would look something like this, where it's just a circle. It's a 2D shape, right? Instead of this thing on the screen, which is basically a stacked cylinder of wire. But the reason I'm showing you this video is specifically because I want to look at the orientation of the magnetic field when we've got current running through a kind of circular shaped coil of wire. So here in a moment, this person is going to turn it's going to make the connection so that there's actually current going through this coil of wire. We see the compass flipping back and forth. Let's see, put it on there. Okay, let me pause. There we go. And you guys can see the orientation of the magnetic field. It's what we would, mathematical term we would use is it's axial. What does that mean? That means it runs along the axis of this coil of wire. If I think about this circular loop, how would it run? Well, along the axis, something like this. All right. So let's stop this share and let's maybe pull up here the PowerPoint for today for this lecture. Oops, that's the end of it. I need to go to the beginning because the beginning is a very good place to start. Yeah, that was a Mary Poppins reference if you didn't catch it. Anyway, circular coil of wire here. If we were able to think about maybe some of the deeper principles and look at the mathematics and do some calculus, we could come up with a formula that would tell us the magnetic field at the exact center of this thing. That formula is, it's right here. It says magnetic field is equal to capital N times mu naught times I over 2R. That's a capital R there. That R is, you might have guessed it, it's the radius of our coil of wire. The capital N is the number of turns of wire that we have. In my little demo thing here, I just basically have one turn, but if I, maybe stacked a whole bunch of wire on top of itself, the number there that of stacks would be my number N. I, of course, is current. Okay, and this formula is only good for telling us the magnetic field at the exact center of this coil. There's additional formulas we could come up with for other locations, but this is good for what we're doing. All right, so one of the things that we need to worry about, of course, is not just the size of the magnetic field, but the direction it points in. And in order to figure out this direction, we're going to use right-hand rule number 2. So there's a little pictorial there at the bottom of the PowerPoint screen that shows right-hand rule number 2 applied to a circular coil of wire. But what I'm going to do is, again, I'm going to stop this share real quick, and I'm just going to try to talk to you guys a little bit here with this demo. And I got to get the distance right. All right, so let's say, and towards my face, not, okay. Let's say that we've got current running around in this direction. Okay, and I want to know the direction of the magnetic field through the center of the coil. Well, if current is running around this way, what do I need to do using right-hand rule number 2? I need to put my thumb into the direction of the current. So that's what I've done there. I put my thumb in the direction of the current, and I need to put my fingers where I'm interested in the magnetic field. And what we see right now is that my fingers are pointing out of that coil of wire. They're basically pointing away from me. They're pointing towards my computer screen. Okay. So if my current is running around this way, then my magnetic field is going to be pointing that way. All right. What about the exterior of the loop? Because it may not just be the interior of the loop that I'm interested in, even though that's the only place we've got a formula to calculate with. I might be interested in the direction of the magnetic field outside the loop. Well, if my current is running around this way, again, I put my thumb in that direction that the current's running in, and then I leave my fingers over here where I'm actually interested in the direction of the magnetic field. And my fingers are pointing towards my face at this point. Okay, so if my current is running around this way, then when I'm over here, my magnetic field is going to be pointing basically away from my computer screen towards my face. Okay, that's what the right-hand rule tells me. Okay, that's what the right-hand rule tells me up here. That's away from the screen. What it would tell me over here, it's away from the screen. What it tells me over here, it's basically away from the screen. Now, if I'm interested in the magnetic field inside the loop, I put my fingers inside the loop, leave my thumb in the right direction, the direction of the current flow, and my fingers are pointing towards the screen. All right, so that is that in a nutshell. Did the whole world just move? No, it's just me kicking the table. That was a joke. Okay. All right. Anyway, we could ask ourselves, oh, well, let's look at the field lines first. If we take a look at the field lines, you'll notice that these field lines really kind of closely resemble the field lines for a bar magnet. So very, very similar. So now let's think about what happens if we've got maybe two of these coils next to each other. Would we feel an attraction between them, a repulsion between them? What would happen? Well, if we apply the lesson from the last lecture, we should be able to think through this and realize that if my currents are running in the same direction in these two adjacent loops, then we should feel an attractive response. If they're running in, so if they're running in the same direction, there's an attractive response. If they're running in opposite directions, and if you don't think this is hard to do, try it yourself. No, I messed up. Anyway, if they're running in opposite directions, we should feel a repulsion. So a little caution on this particular slide. Those bar magnets that are inserted in the middle there, those are just there to show you basically the direction of the magnetic field that these current carrying wires are generating. They're imaginary. They're just there to help us in understanding the direction of the magnetic fields. So at any rate, if we've got currents running in the same direction, there's an attraction. Currents running in opposite directions, there's a repulsion, just like with the long straight wires that we talked about in the last lecture. All right, awesome. So let's go on to a problem. We've got a circular coil of wire, really close, actually laying so that its edge is right on top of a long straight coil of wire, or a long straight wire. So a circular loop near a long straight wire. We're given the currents through both loops, or the currents through both wires, excuse me. And we are given some of the geometry. And we're asked the question, well, what's the magnitude and direction of the net magnetic field right at the center of the loop? Now, we certainly have enough information with kind of the formulas that we've learned in order to figure out the individual magnetic fields. This is the magnetic field. What I've drawn there is the magnetic field of a long straight wire. That's the formula for a long straight wire. And let's identify our variables. Let's see, our long straight wire has a current of 8 amps. Mu naught is a constant, 4 pi times 10 to the negative 7 Tesla dot meter per amp. The only other variable I have there is that R, and that R is the distance between the long straight wire and where we're interested in the magnetic field, which is right smack in the center of that loop. Well, that R is going to be the exact same value as the radius of my coil, which is given to us. It's right there. All right. So I can plug those numbers in and figure out the value of the magnetic field due to wire 1. See, it's got an I1 there. For wire 2, well, what's our formula? B is equal to N mu naught I, and maybe I'll add in here some subscripts. Why not? There we go. Use your imagination. That's supposed to be a 2. All right. So capital N in this case, it's just one loop of wire. There's no multiple turns or anything like that. So N here is 1. We're certainly given the current in that loop of wire, and we're given its radius as well. So we've got everything we would need to plug into that formula for the magnetic field at the center of the circular coil of wire due to the circular coil of wire. So we could get numbers for B1 and B2, and we'll do that in a minute. But one thing we have to think about is, well, we've got 2 different magnetic fields. How are these going to add together? Because we remember that magnetic fields are vectors. So we have to worry about how these vectors are going to add together. All right, so on the next slide, I have a question for you. I've asked, okay, at that point that's identified, which is marked with a C, what are the directions of the magnetic fields due to the long straight wire and the loop of wire? So I want you guys to pause and to think about this, come up with a response, and then we'll talk. So pause. Talk about your awkward silences. Anyway, what do we see? The correct answer is choice C, that the straight wire has a magnetic field that's out of the page at point C. The loop of wire has a magnetic field that's into the page. So let's look at those maybe individually because we might be confused about this. Okay, so let's look at our long straight wire. Our long straight wire basically has a current there that's going downwards. And if I think about my right hand rule number 2, and I put my thumb downwards, and I'm interested in what? The magnetic field on the right hand side of that coil. And I do exactly what I'm doing here. I'm using a pin as my long straight wire, actually my stylus. And then putting my thumb downwards in the direction of I, and putting my fingers on the right hand side of I where we're actually interested in the magnetic field. My fingers are pointing away from the screen. This is I is out of page, or excuse me, B is out of page. So this is I1, this is B1. B1 is out of page or out of screen or whatever. All right, so that's that one. Let's think about now the circular loop. So let me clear my drawings and let's look at the circular loop. All right, so the current is going this way. This is I2. All right, now if we think about that circular loop, so here's my circular loop. And again, I know this looks odd because I'm staring at a camera, you're staring at a screen, but I'm a student sitting here watching this. What am I doing? I'm picturing a circular loop. I'm putting my thumb in the direction that the current's going in. I'm setting my fingers in the center of the loop, and my fingers are pointing away from me. Okay, so so the current here is, or excuse me, the magnetic field here is going into the page. So this would be going into the page for B2. That means that B1 and B2 are pointed opposite of each other. So they're not going to just add together. We're going to figure out, well, which one's stronger, and then whichever one's stronger, that's going to rule the day, and we're going to have to take the difference between the two to figure out my net magnetic field. That's exactly what we've done here. So we have, figured out that the magnetic field is going to be the difference between the two individual ones. We've plugged everything into formulas, and then we have gotten our result, which is, change this, which is right down there. This is our net magnetic field. B net is 1.1 times 10 to the negative 5th Tesla. This answer, though, is actually, honestly, this is incomplete because it doesn't state the direction. And if I were going to do this, I would just want to state that the direction is out of page. Okay. Which hopefully you guys can see what I mean here. I know that drawing is a little weird on the screen. If we go back and we think about the way that I had drawn things on the last slide, where there's our two currents. And so we're just picturing these as being in the plane of the screen. I1 is going to, or B1 is going to be out. B2 is going to be in. B1 is bigger than B2, so B net is what? B1 minus B2. And then we see the result down at the bottom. This is 1.1 times 10 to the negative 5 Tesla. And this is out of page. All right. I believe that that is it. We will see. That's it. Yeah, that's a nice black screen. All right. Thanks, guys. I will talk to you about solenoids in the next lecture here.